Dr. Arash Dehzangi. He was born in Shiraz, Iran. He accomplished his master's degree thesis in the University of Shiraz. He has worked as a tutor and lecturer in several universities in Iran during 1999 to 2008. After that, he joined the University Putra Malaysia as a PhD student in nanosciences, focusing on nanotechnologies, and graduated in 2012. Since August 2012, he joined Institute of Microengineering and Nanoelectronics IMEN of National University of Malaysia, UKM, as a post-doctoral fellow.
In the name of God. Thank you everybody for coming. I'm so delighted to get a chance to speak with you about my project. I'm very welcome you for coming here, and I know the limitation of the time and got so bored during this time. So I'm just going to skip some parts of my presentation and get just the main part and major parts of my presentation. As you know, my name is Arash Dehzangi. The title of my presentation is Fabrication of Junctionless Silicon Nano-Transistor SOI by Atomic Force Microscope Nano-Electronics. Right now I'm working with the IMEN from the University Putra Malaysia, Putra Malaysia. The outline of my presentation is composing of this first introduction, go for introduction of the junctionless transistor, objective, method, result, and then conclusion. So let's talk about the transistors. First I'm going to explain about why actually we're going to scale the transistors. So it's good to also have the presentation of my friend about the cell phones. So why the cell phone is getting so smaller during last 10 years. So this is kind of give you the response, the answer of this question. So transistor basically is derived from two words, transfer and resistor. Basically it's the three terminal devices which the current between two of these terminals is controlled by the third one. So the main purpose of the transistor is to control the electric current. The basic and the very first transistor established in 1925 by Mr. Lennington in the United States, and he called this device as a device for controlling the electric current. So the device for controlling the electric current, this is the thing that we can define the transistors. But the practical transistor was established 20 years after that in 1947 at the Bell Laboratory by the William Shockley, John Gardner, and Walter Pitay. The main thing that I'm going to access on right now is about the p-n junction. The basic and the most common type of the junction that nowadays using in transistors is the p-n junction. So what is the p-n junction? Before I'm going to explain what's the p-n junction, let's start about the scaling the transistors. So let's talk about the Dr. Morse. The Gordon Moore was the manager of the Intel company in 17 decades, and he predicted that the number of the transistors on a certain chip is going to be doubled after 2 years. So after a year, this prediction turns to be as a Moore's law. So you can see here and this graph the trend during last 20 years. What happened into the computers and the PCs and the digital devices. So you see that the memory, the red one shows the memory. So from the 1K turns to the 4 giga in 2010. So this is the consequence of the scaling of the transistors. Since you can get the number of transistors doubled in a specific chip, it means that the speed of the transistor is going to be doubled. The capacity, the memory, of course, the most important is about the memory and the processing. So you see that from the 4004 in 1970, we got to the Pentium 4. And nowadays, you know that we already passed the Pentium 4. So this trend of scaling and shrinking the size of the transistors is the consequence, is the origin of this this, I think, the explosion of the very, very small devices with high capability and with the high performances. So the smaller dimension, I mean about the size scaling of the transistor, directly gives to these three consequences. They first increase performance, faster circuit operation, and the reduced power consumption. So the reduced power consumption means less price and low costing. So you can have more effective and more efficient devices with less price. So what's the junction? So you can see here, I'm trying to explain it as fast as possible about the junction. Junction is the two different type of the semiconductor attaches to each other. One of them holds the positive charge, the other one holds the negative charge. It attaches the junction between these two called the p-n junction. Each transistor holds two junctions, you see that. Basically, this is the MOSFETs, of course, but for the another structure of the transistor that we got here, so we got a little bit different structures. But basically, we use the junction for all of them. But the shape maybe is not really the same as this one that I have chosen here, but the performance is the same. So you see, normally we have two junctions here. So the current goes from the source to the drain, and it's the gate that controls the current between these two contacts. So after the scaling of the transistors, you see that these two junctions gets very close to each other because we want to move on from the macro size to the nano size. So you see that these two junctions, for example, source and the drain, get very close to each other when we want to get to the nano scale, 50 nanometer, 100 nanometer. So when these two junctions get close to each other, we got this overlap problem. So, and shortly, we call it short channel effects. This is the problem of the junction in modern devices. So, ultra sharp doping concentration. Doping means we need to deposit a lot of charge here because then the size gets smaller, so we need extra charge to have a carry. So, we need to deposit and dope the charge into the devices. So, the processing thermal budget, the costly millisecond, because when the size is smaller, so we cannot anneal it. Because for activation, we need to heat the device. So when the size is so small, so this heating is kind of so tricky. So we got to control this heating part. So it's really costly. And the last but not the least is the short channel effects. Short channel effects means this overlapping between these two junctions, which really limits the performance of the device. So what's the junctionless transistor? Simply, they remove this junction. So you can have a simple comparison between the junction transistor and junctionless transistor. So there is no junction here, and this is uniformly doped. So it provides higher speed, it provides low cost, and of course, low power consuming. The very first junctionless transistor established in 2010 by a famous paper, article by Dr. Kulin in Nature. And after that, a lot of groups goes for extending the application of these kind of devices. So the objective of my work and my colleagues' work, of course, we were a team. It was about to investigate the fabrication of this kind of transistors by the specific way, we call it atomic force microscope method, by local anodic oxidation, LAO. From now, I'm going to call it AFM-LAO, about as a summarize of this very long method. So there are several advantages. I'm not going to bore you with this kind of things. So the process is something like that here. AFM, or atomic force microscope, has a very little tiny tip. It goes on the surface of the chip or any samples, apply a voltage between this tip and the substrate, and at the presence of the water meniscus and water drops in the air, there would be some oxide layer above. Then we can use it as for several applications. One of them here as a mask. So this is the AFM tip, goes on the surface. You know that the substrate is silicon uninsulated. Very thick layer of the silicon is here. So we apply a voltage, we make the oxide. You know that schematic process of fabrication is illustrated here. You can see that. We make oxide here. After that, we remove the silicon by the chemical etching here. And after that, we can remove this oxide layer, so we got the device. So the method goes from the AFM nanolithography, chemical etching, and after that characterization of the device. So the atomic force microscope has a lot of advantages, a lot of benefits, which I'm not going to bore you with this, so I'm going to skip this and get to the work that we have done. So there are a lot of parameters need to be optimized. For example, the voltage that we apply. You can see here the AFM image of the effects of the applied voltage on the surface of the silicon. You see that different voltage provides different effect on the surface. So this is the profile. So the thickness is about 2 or 3 nanometers. Or the speed of the tip. When the speed goes faster, of course the effect will be less. Then here you can characterize the effect of the writing speed on the surface of the silicon. Or the humidity. Relative humidity is really important. Since I mentioned before, the water meniscus and water drops in the air is really crucial for making this oxidation. Also, because we are dealing with the nanoscale, so the cleaning process is really crucial. I think we are talking about 5 nanometers, so you cannot imagine how clean the wafer must be. Here, the effect of the etching process. We performed a very critical and very precise etching process because it works in the nanoscale. So we use potassium hydroxide as a main chemicals for the etching process. We checked it for different samples, for different structures. And you can see that this is the structure that we made. So, for example, I took one of them. So you can see here the effect of the time of etching on the structure. And here you will see the structure after the etching process. This is the very simple transistor. So here the overall optimization can be seen. Here, this is the mask. AFM make this mask after the removal of the mask. A removal of the silicon, we got the structure. This is source, this is drain. Current goes from source to drain, and the gate from 2 sides is going to control it. And here, you can see, I think this is the most optimized. Here, this is the device, source and drain. The current goes between source and the drain. The nanowire installed here, less than 100 nanometer. This is the profile of the nanowire. And you can see this is the gate, and this is the gate which controls the current between this area. This is the size. And this one is the profile. The profile of this nanowire, which we cut it by high resolution transmission electron microscope. You see that. It's about the size. This is the profile of the silicon. So basically, this one is this. So it's trapezoidal. It's not the square shape. So after the removal of the silicon at the size, this is the profile of the nanowire after the whole etching process. And the current goes through this path between the source and the drain. The conclusion is that for the first time, we fabricated the device by atomic force microscopy. The device, I mean the junctionless transistor. Of course, the principle of the junctionless transistor already established. But we were the first time, our group and my colleagues, that fabricate the junctionless transistor in the world by this method. Which, after that, of course, the fabrication is just a small part. It goes for the characterization, it goes for the IV characteristic of this device, and most importantly, we need to know what exactly is going on underneath. We go for the simulation of the device and compare it with the experimental measurements. This is the publication that specifically we got from this project. 4 Q1 papers with the really high impact factor, and the 2 Q1 papers during the last 2 years. So the awards that luckily we can get, the students here know that sometimes it's really difficult to get the award and grant here for improving the project. So this is some of the grants that fortunately we can achieve during these 3 years. And at last, I would like to acknowledge my colleagues here because running the nanoelectronics, not only in Malaysia and every part of the world, is really difficult. So we cannot claim that this is my personal or 2%. There are several persons that working, so I'm going to acknowledge their work and their help. Dr. Laki from the IMEN, Prof. Burhanuddin from IMEN, my supervisor, Dr. Mutagallim from USM, because the whole project was performed in USM University. and Mr. Makarim Abdullah from Sirin Berhad, and Prof. Dr. Nizar from the UPM Electrical Engineering Department.